Yeah, so in this video, we're going to look at the following expression. The problem here is x cube, x, x cube plus 2x over 2x plus 1 is BigO of x squared. Okay, so what does this mean here? It means that if this expression in yellow is true, then there must exist some constant c and some constant k, where c and k are positive constants, such that x cubed plus 2x over 2x plus 1 will be less than or equal to c times x squared for some x being greater than k. Okay, here is the definition. This piece over here is just the definition of BigO. Okay, so here is the definition for moving from this piece in yellow to this piece in green. Okay, so what we'll do first is we'll start with the graph. We'll start with a graph to get an intuition whether this expression over here is actually true. So I'll open up Wolfram Alpha, and on Wolfram Alpha, what we'll do is we'll first plot these expressions in yellow, which is plot x cubed plus 2x over 2x plus 1 and plot x squared, which is my function g of x. I'm going to say this is between, let's say, 0 and 5. So when I plot this, I can see on my curve here that that my red function over here is x squared. My red function over here is x squared, and the function in blue over here is x cubed plus 2x over 2x plus 1. And the question was whether this entire statement is actually true, meaning is f of x BigO of g of x, where g of x, where this entire piece g of x is the function, is this function over here, x squared, and this f of x is my function over here. Okay, now you can see that the function in red is basically going to be the upper bound, on the function in blue, and this shows you that the expression f(x) being big of g of x is actually correct. This is correct for what values of c? Well, in this case, c happens to be 1, c equals to 1, and what values of k? Well, the values of k where this makes it true is over there. For this value of k, whenever x happens to be greater than k, whenever x takes on values that happen to be greater than k, at every single value of x that is greater than k, the red function will be an upper bound on the blue function. Okay, so the statement is actually true. Okay, now what we'll do is we'll apply the calculus approach, the limit approach, and see whether that makes sense as well. So let's go back to our board over here, and what I'll do is I will just take x cubed plus 2x over 2x plus 1, and I'm going to divide this. I'm going to divide both the sides of this inequality with x squared, and that gives you the following expression here. Okay, so now the numerator over here is x cubed plus 2x. The denominator here is 2x cubed plus x squared. Okay, and now what I would like to do is I'd like to look at this. I would like to look at this entire fraction and see what happens to that fraction. What happens to the fraction as x goes towards infinity. As x goes towards infinity, does the limit exist? Okay, and I'm trying to address the question: does the limit for this piece? Does the limit of x going towards infinity exist? Okay, so let's try this. So when I plug in x is infinity, well, one thing I can see that this happens to be an indeterminate form of infinity over infinity. So this becomes infinity cubed plus 2 times infinity, that's the numerator, which is infinity, over, again, infinity cubed times 2 plus infinity squared is also an infinity. I have an indeterminate form. The moment you have indeterminate form, I can make use of the following expression, which is the L'Hopital's rule. So limit of x going to infinity of f of x over g of x is equal to limit of x going to infinity of f prime of x over g prime of x. Okay, let's take the first derivatives. If I take the first derivative of the numerator, this piece over here in pink is f of x, and this piece over here in green is g of x. And I'm just going to apply the definition that the limit of this thing is also equal to limit of x going towards infinity of f prime, which is the first derivative of the function f of x, and g prime of x is the first derivative of the function g of x. So the numerator becomes 3x squared plus 2 over 6x squared plus 2x. And I can see that the moment I plug in x as infinity in this new expression, I still get the same issue of an infinity over infinity expression. So I can make use of L'Hopital's rule again, and this is going to give you, if I take the first derivative again of this new function, this is going to be 6x, and the denominator is going to give you 12x plus 2. And the same idea, I take the first derivative again because I still have an infinity over infinity form. This becomes 6, and this becomes 12, 2, and I can see that the limit over here is actually half. The limit of this entire function, as x goes towards infinity, this limit does exist, and the limit is 1 over half, 1 over 2, which is half. Okay, so as long as I choose any c that happens to be equal to half or greater than half, then g times x over c will be greater or equal to the function f of x. Let's try this. Let's go back and plot this and see whether this actually holds true. So I'm going to open up my Wolfram Alpha here, and let me pull up a Wolfram Alpha, and let's just quickly plot these again to make sure that does that C guarantee an upper bound. So if I plot here, if I plot x to the power 3 plus 2x over 2x plus 1. So this is a function over here. Let's also plot x squared between 0 and 5. Okay, so what's the c that I'm currently playing with in this problem? In this question, c happens to be 1, but I'm just saying x squared. The constant that I'm multiplying x squared with is c, which happens to be 1. And that's okay because this value of 1 is greater than half, and because it's greater than half, I do have an upper bound of the g of x on the function x cubed plus 2x over 2x plus 1. Now, if I choose any other value that also happens to be greater than 1, such as 2x squared, that's okay because the red function will continue to be an upper bound. But the problem comes when I choose a value of c that happens to be less than half. So let's put maybe 0.3 here. If I put 0.3 there, then the red function at this point starts to behave as a lower bound. It's not acting as an upper bound anymore, and this is because I have violated the inequality of c not being greater than half. Okay, so c must be a value that happens to be at least greater than half, and the c that I've chosen over here is 0.3, and this 0.3 is definitely violating this inequality. Okay, so here I can kind of use my ideas of limits and plot them to see whether the graphical interpretation of BigO is consistent with the calculus interpretation where we start using limits.